Hello once again. Thanks for joining us on Space Nuts, where we talk astronomy and space science and all sorts of other interesting and wonderful things, including supernovae. We're going to answer audience questions today, and our first one will be about that. We'll also be talking black holes. It's odd that comes up in an all-question episode. We've also had questions about something that someone heard about in Australia back in the 90s and wonders if it's still happening. I can answer that one. And Fermi Bubbles and Mars and dark matter and all those sorts of things coming up on this very episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us as always is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you today?
Oh, gosh. How can I explain it? Busy. Yeah. busy.
Still looking empty behind you.
Yes. Done more and more packing and getting ready for the big move, which is only a few weeks away, and we're it's flat out. Unfortunately, my wife has hurt her back. And that's
it's not what you want for a move.
No. But these things happen at our age. You still think you're 30 and you're not. So things break. Yeah. Or get stretched beyond their limits, I think would be a more apt description. But yes, couldn't have been worse timing. But yeah, if we weren't moving, it probably wouldn't have happened.
No, you never know. That's right.
Now, how about you? What's happening in your world?
Busy as always. Lots going on. I thought I might just mention, and maybe we've got listeners in Maui.
Yeah, I think we've got one or two
in Maui.
Oh, Maui, yeah. Gosh.
Because Lahaina is one of mine and Marnie's favourite places in the whole world. We've had many, many happy holidays in Lahaina. And so we've been devastated to see the pictures of what it looks like now. You probably remember we got married on the top of Haleakala, which is the extinct volcano nearby. And, of course, the connection with astronomy is that there are telescopes on the summit of Haleakala, including some quite significant ones.
Pictures coming out of that region are just unthinkable.
They are, aren't they?
And we know what that's like. We've had that happen in our region twice in the last several years. Some huge catastrophic fires wiped certain towns off the map completely. Certainly threatened the Siding Spring Observatory there, and not just threatened, did do significant damage to the visitors centre and the accommodation block. Fires are a common thing in this country, and we are all too aware of them. So our thoughts and prayers certainly go to the people of Maui, and it's all you can do is shake your head and wonder how it happened.
How they're going to rebuild as well.
It'd be so difficult.
There was a few fantastic fish and chip shops in that street that's not there anymore, and other lovely places to shop. In fact, most of the clothes I wear came from shops in Lahaina, which is a bit weird. It's very, very sad indeed. Very sad.
True. They will rebuild, though.
They will, They're people with stoicism and persistence, and it'll come good. And I hope Marnie and I'll find our way back there again sometime not too far down the track.
Yes. Beautiful part of the world. Let's go to some questions, Fred. And our first one today comes from Sandy in Melbourne.
G'day, Andrew and Fred. It's Sandy here from Melbourne again. My question today is about the newly discovered supernova in the galaxy M101, also known as Pinwheel Galaxy, as I understand. The Pinwheel Galaxy is around 21 million light years away, and the supernova is so bright it's visible with a relatively small telescope, as I understand. How bright would a supernova be if it were to happen closer to home, such as around 4 light years away, the distance of Alpha Centauri? Would it be so bright that it'll be visible as a as brightly as our moon during the daylight hours? Or would it be so close that we will be essentially toast? Thank you again for such an awesome show, and look forward to hearing the answer. Thank you.
Such a positive question to start on. Would we be toast? It is a really interesting question, and we're constantly on the lookout for these things. And there's a couple of brewing that I'm thinking about. So, how close is too close? What would it be like if one went off around Alpha Centauri? Yeah, that's a good question.
We'd be toast.
Oh, would we?
Yeah. Probably at that distance, yeah. At that distance, we'd be probably fried by neutrinos. Sorry, there's a jet going by very low.
Oh, okay. Probably trying to stay under the rains.
Maybe
today.
so. Yeah. So four light years is too close for comfort for a supernova explosion. Betelgeuse, the star that's kind of keeps sending out clouds of dust that make its brightness drop. I think that's about 500 light years, roughly.
Yeah.
And if that turned into a supernova, it would be marginal that we would have any deleterious effects on Earth. I think we would be at risk even with that. The other one is the Eta Carinae, which is a star in the constellation of Carina, the Keel. Passes overhead here in Australia once a day. That is about 8,000 light years away. And I think we would probably see it in some comfort, although if it turned into a supernova, it would still be bright enough to see in the daytime sky.
That's incredible.
Just as Sandy has said. Yeah, they're not things to be messed with, aren't supernovae, because they are so energetic, so much happening. And the radiation that they emit across the electromagnetic spectrum and in the particle domain as well is pretty overwhelming. Lots of it.
It's just hard to imagine something so cataclysmically enormous.
Yeah.
Being able to do such devastation over such wide areas. It's unthinkable.
Yeah, yes, that's right. It's because that's the thing about a supernova. Their radiation is not like things like pulsars, where the radiation's beamed on a kind of lighthouse beam and it's rotating. With a supernova, it's isotropic; it's going out in all directions, and there might be some directions where it's stronger than others, depending on the way the collapse occurs. But as the star collapses into a black hole or a neutron star or whatever the end product is going to be, but it's very energetic, and as I said, we don't mess with them.
No, just. Let's say it did happen 4 light years away. Would we have any warning whatsoever, or would we be, toast by the time we discovered it?
Well, we would know that there was a likelihood of this particular star. Supposing Alpha Centauri was more like Eta Carinae, it would be monitored day and night, probably in great detail, to look at what was happening. There aren't any stars in the Sun's neighbourhood that are like this, highly evolved and highly massive stars that are going to undergo a supernova explosion. So you can be, the Alpha Centauri system, it's more than one star, but they're all pretty stable stars. They're not ones that are likely to do anything like that unexpectedly. So what I'm saying, I guess, is that it would be a particular type of star that would put us at risk of a nearby supernova explosion, and Alpha Centauri isn't one of them.
Yeah. I did see a report fairly recently that suggested Betelgeuse could go gangbusters sooner than they thought. I don't know how much credibility is in that claim, but it did seem that the question has been asked as to how much sooner it may, burst its bubble.
Yeah, it could be 10,000 rather than 1 million years. That's the problem. Is you just don't know that.
No.
I think my kind of reading of the situation in the astronomy press is that I think most scientists are fairly relaxed about Betelgeuse. It's certainly a potential supernova, but I think they think we've got a while yet.
Yeah. And what about Eta Carinae?
Hard to know. May even have gone off already, Andrew.
Yeah, well, that's the thing.
It's 8,000 light years away. It's got 8,000 years before the light gets to us.
Yeah, but what if it was 7,999 years ago?
Could be arriving, yeah.
Could be.
Yeah.
I
think even then, though, you'd have some idea that things were getting disturbed and we were likely to see something happening.
Yeah.
Within the next year, if it was 7,999 years.
If we had fair warning, would it be possible to say, get ourselves underground and protect ourselves from the radiation and, stick around there for as long as it takes to get back out and get on with our lives?
Yeah, you're right. It becomes a civil defence issue. I think if you're on the side of the Earth that's facing away from the supernova, you've got a better chance of being on the side of the Earth where you're not, where you are facing it. But yeah, underground might be good.
Yeah, or just wrap your house in aluminium foil.
Oh, you need to wear it on your head, of course. You've got to have,
yes.
Got to have
or
that.
just line all your clothes with it.
Or as we used to be told in the 1950s in the UK, a paper bag would do it as well.
Paper bag, or get under your school desk.
Yes,
that used to be the way to deal with a nuclear attack, wasn't it?
Exactly.
Get under your desk.
Yes, climb under your desk.
All right. Thank you, Sandy. That's a good question, and the answer is probably yes on all counts by the sound of it.
Yeah, that's right.
As horrifying as that sounds. Let's go to Sweden, and here's a text question from Johan. Hi, guys. One from your Patreon supporters. Oh, thank you. Much appreciated. Love our Patreon supporters. And I have a question about photons that's been bugging me for a while. My understanding is that even single photons can have a wavelength, e.g. gamma or radio. The first one can damage your DNA while the other is harmless to humans. But what's the difference, or what differentiates between them? Both have zero mass and travel at the speed of light. Where does the difference come from? All the best, Johan in Sweden.
Just the different amount of energy that they carry, because the frequency is what determines the amount of energy. Lower the frequency, the lower the energy that this thing will impart whenever it is absorbed by something else. And so, yes, gamma rays are absorbed by human tissue, and it don't do them any good. So it doesn't do the gamma rays any good either. But it doesn't, or the gamma ray photons. But yeah, it's just all about the energy level.
Okay, so there are nasty photons and not so nasty photons.
Yeah, that's right. And it's probably just as well that the Earth's atmosphere protects us from the nasty ones, which include ultraviolet as well as X-rays and gamma rays.
Yeah,
highly absorbed by the Earth's atmosphere.
But the atmosphere isn't strong enough to save us from a supernova.
No, that's right. The intensities are so high that atmospheric attenuation. In fact, I think the atmosphere could get ionized, so it knocks the electrons off the atoms.
Okay,
it's not a pretty sight.
No, no. But we do the human thing and joke about it anyway, don't we?
Yeah, that's right. Yeah, we've probably got a dad joke somewhere about that.
Probably,
Yes.
Yeah. So avoid gamma rays. What other ones should X-rays? Stay away from them.
Yes, that's right. As the early investigators of X-rays, Professor Röntgen in Germany and others discovered when they got sick because they've been tinkering around with X-rays.
Yeah. I suppose that's happened in science off and on.
Yeah,
over time, where you're doing things and you don't realise you're exposing yourself to these situations until you realise you.
That's right, and it reminds me of Alan Alda's story. The star of MASH. Alan,
yes,
is that his name? Yeah, Alan Alda.
Yeah, Alan Alda,
who became very much a very prominent science communicator, got really interested in science, followed up on lots and lots of interesting ideas. He wanted to write a book about Marie Curie, who was one of the pioneers of radioactive materials. And so he went to Paris to ask to see her original letters. And they were all locked up in this lead case, and he couldn't see them because they're so radioactive.
Sorry, what did he go to see? Because you just dropped out.
Oh,
briefly.
I'm sorry. Yeah, Marie Curie's letters, which letters, written about the research that she was doing. These went out to various places, but with them they carried radioactive isotopes, so they're all radioactive. So Alan Alda couldn't access them because they were radioactive. Wow. So he did a book on Einstein instead.
Wow, that's amazing. Yeah, that'd be hard to read. At least you wouldn't have to use a light at night.
No, that's right. No, they were too dangerous.
Yes, indeed. Wow, that's quite incredible. I never realised that. Thank you, Johan. And we've got an audio question now from Dan.
Hello, gentlemen. Dan here from the Gold Coast in Queensland. My question is, if you were floating in space by yourself and you were drifting towards a black hole, how long would it take for the effects of the black hole to start affecting you the closer you got? And from there, next part is, how long would it take for you to reach the event horizon? Are we looking at years, or does time dilation kind of warp how you perceive that? Is there no real way to answer that? All right. Cheers. Thanks for all your hard work. Bye.
Thanks, Dan. I think we kind of alluded to this situation last week or the week before, but I suppose it's all relative, and has a lot to do with proximity and where you are observing things from.
That's right, and your speed. That's the thing. Sorry, our puppies decided to celebrate black holes there in the background. So I think I might have mentioned there are stars which are happily in orbit around the black hole at the centre of our galaxy, whose distance from the black hole are kind of solar system distances. They're measured in a bit more than solar system distances. They're measured in trillions of kilometres, whereas we think of the planets being in billions of kilometres, or at least the distant ones. So so you can be in orbit safely around a black hole. That would change if these things were not moving fast enough to stay in orbit. So it's all about what speed you're doing as well. If you fly past a black hole at a fast enough speed, it won't pull you in. Although as you approached it, you would start to see relativistic effects. And I think the spaghettification would start at quite a significant distance from the black hole. In fact, I don't know whether we mentioned this when it came up before, but there is a gas cloud that's currently being spaghettified by the black hole at the centre of our galaxy, which has been observed with radio telescopes, and its shape is changing. It's getting elongated as it gets pulled in towards the black hole. And I can't remember the distance of that, but I think it is measured in trillions of kilometres rather than millimetres. So
that's another thing that has far-reaching effects.
Yes, it is. Well, it's gravity. Gravity goes on to infinity. It falls away in intensity, but it never stops. So you're always, in some great gravitational field or another.
So I suppose I'm sort of steering away from the question of black holes, but does that mean perhaps that gravity does have some sort of relationship with dark matter?
That it certainly does, because that's the only thing that dark matter reveals itself by, is its gravity.
Yeah.
Unless we've got Newtonian dynamics wrong, which we sometimes talk about the modified Newtonian dynamics theory, which is a suggestion as to how we might have got dark matter wrong. It's if accelerations don't behave like Newton predicted at very, very low levels. And actually there's some research that's in the in the wind at the moment. It's more than that. It's been on the interweb quite notably. This is to do with binary stars, which are widely separated, which means they exert small gravitational forces on them and allow you to test the idea at low accelerations, the idea of MOND, modified Newtonian dynamics. And it's looking a bit more promising for MOND. So, yeah, interesting stuff.
Yeah, fascinating. And apologies for the dropouts. We're having a few.
That's interesting. I haven't noticed any from you, but you've obviously had some from me, which is
just a couple. But yes, hopefully we can sort all that out at the other end of things. So Dan, yes, a fascinating issue that you've brought up, but basically, it depends how fast you're going and point of view, etc. But the effects of a black hole are far-reaching, as they are with supernovae. Yeah. Thanks, Dan. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Yep, that's us. And we are going to go straight to our next question. This is Buddy from Oregon, I think. Here we go.
Hello, Space Nuts. Buddy from Oregon. Hello, Fred and Andrew. Hey, can you guys tell me what happened to that? I remember when I was a kid, about the only news I ever heard out of Australia was about the race with the solar-powered electric cars. And it seemed like in early 90s, I think it was, GM entered and beat everybody by quite a ways. And did the race continue after that? Whatever happened about that? I heard GM made an electric car after that. If you look into that, you might notice that might be a little bit of a rabbit hole. Anyways, thanks, guys. Love the show.
Thanks, Buddy. Do you remember the Solar Challenge, Fred?
Yep.
I think it's been around since the late 80s, and it was Hans Tholstrup, if I recall correctly, that won the first race and drove his solar car from Darwin to Adelaide, wasn't it?
I think that's the route, either that way or the other way. And you're right, that's the difference. They're not just electric cars; these are solar-powered electric.
Solar-powered, yeah. I remember his car, that very first one. It just looked like a little bullet on tiny little wheels, had no suspension. I think it was just like driving a coffin, basically. And it wasn't much bigger than that. But the whole aim of the race is to use the sun's power to drive your vehicle. And they choose that part of the world because it runs in October, which is when you get much more sunshine, and it's the best time of the year for the race between those two centres. But terribly hot driving across Central Australia that time of year. Worse later in the year. Yep. But Buddy, to answer your question, it is still going. It is still an annual event, the World Solar Challenge. You can look up their website because it is coming up again from the 22nd to the 29th of October this year. Darwin in the Northern Territory to the capital of South Australia. So you're basically going from the Gulf of Carpentaria to the Great Australian Bight, basically north to south across Australia, Central Australia, Darwin to Adelaide. It's a massive event, and it was originally designed as a sort of a test bed. There you go. 1982, solar pioneers Hans Tholstrup and Larry Perkins embarked on a quest that would see them drive a home-built solar car, Quiet Achiever it was called, across Australia from west to east originally. There you are. Inspired by this achievement and his own pioneering vision, Hans urged others to explore the boundaries of sun-powered transport, and the World Solar Challenge was born. So the first race, if you like, was inaugurated in 1987, and they've been basically racing across Australia ever since. It is a fantastic event, and I suppose it was instrumental in getting the focus on other forms of power away from fossil fuels. And look at the situation today. Okay, we don't have solar cars driving around all over the place, but we do have solar panels on the roofs of a great number of homes around the world. Alternative energies are becoming more and more prominent. And this race was one of the reasons all that started. And of course, the advance in solar panel technology is changing very rapidly. We've got solar panels on this roof. We've got 19 of them, I think. And to get a bigger system than mine now will generate more power with only 16 panels. And we're talking 5 or 6 years time difference. It's just become so much more advanced, and it'll just keep developing. The standards are so high. But Buddy, your question was well placed, and yes, you'll be very happy to know that they're running it again in October. It's a Teams event, and they have scrutineers. The cars all have to meet certain standards, just like any motor vehicle race, and they have to operate within the regulations of the competition. And it's all very highly professional and sponsored these days. And I'm also amused that that's the only news you've ever heard come from Australia, because I think we've done a few other things over the years, but there it is. Yes, we still run the World Solar Challenge every year in Australia. Thanks, Buddy. Let's move on to our next question. This one comes from Robert in the Netherlands. Hello, guys. Love the podcast. That Aussie accent is a lot of fun. And well, Fred doesn't have an Aussie accent. And I so love the grandeur of astronomy. Thanks so much for informing us. My question, how do you guys feel about the implications of the discovered Fermi Bubbles? There was a Japanese professor who recently ran simulations proving they are produced by our very own Sagittarius A star. Do similar bubbles probably appear in every galaxy with supermassive black holes? And are they inferior? Are they therefore perhaps linked to the dark energy problem? Given their sheer size, could they somehow be responsible for the missing gravity effects? Thank you so much for answering this, for it's not elementary, my dear Watson. Yes, I am funny. No, you're not, Robert. But anyway, thanks for the question. I appreciate the joke. Fermi Bubbles, you better explain what they are first, Fred, and then find out whether or not Robert is on the money.
So these are structures around, not far from the centre of our galaxy, which are visible in gamma rays. So these are, we were talking about high energy photons being gamma ray photons, as a couple of minutes ago, as a comparison with how the energy of different photons varies. So the highest photons are gamma ray photons, and we see gamma ray observations of the sky from various satellites. Most notably the Fermi satellite, which is why they're called Fermi Bubbles. These things are structures which look like giant bubbles above and below the center of our galaxy. And they stretch up a total length of about 50,000 light years. So kind of 25,000 on each side of the center of our galaxy. That's more or less a quarter of the diameter of the galaxy. It's huge. These are huge structures. So the explanation as to their presence is, yes, absolutely to do with the supermassive black hole at the center of the galaxy. And so that the black holes, these black holes at the centers of galaxies, when they are actively gobbling stuff up, they produce jets perpendicular to their accretion disk, the disk of material that's being swirling into the galaxy. And that's when they get very bright in things like X-rays. And our galaxy currently is quiescent in that regard. There's not that much going on. It's about to eat up a gas cloud, as we were talking about a few minutes ago, which is being spaghettified. But the jets of material that they squirt out are quiet at the moment, if I can explain it as fountains of high energy particles. So in a way, the the Fermi bubbles are like fossils of previous activity. So it's when our central black hole was energetic in the past that these jets of material squirted out, and their interaction probably with the interstellar material in the galaxy is what caused the gamma ray activity and making these Fermi bubbles. So really, an interesting aspect of our galaxy that was unknown before we had gamma ray telescopes in orbit.
Oh, okay. Is that it?
Pretty well.
Okay.
Yeah. Sorry.
That's all right.
I should have shut up for questions there.
No.
We have, I think, talked about Fermi bubbles before.
We have, yeah.
And I think the question about whether they exist in other galaxies is yes, I think they probably do. They may be, I'm not sure how far away you can detect Fermi bubbles from. So, a distant galaxy a few million light years away, these things might be too faint for our gamma ray telescopes, but I'm sure they will be there, even if we can detect them or not.
Okay, very good. Thank you, Robert. Lovely to hear from you. Keep the jokes coming, but work a bit harder on them if you don't mind. Yeah. This is Space Nuts. Andrew Dunkley with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, to our next question, Fred. This one comes from, he always seems to pop up every 5th episode, does Martin?
Hello, Space Nuts. Martin Berman Gorvine here, writer extraordinaire in many genres, with a question about everyone's second favorite planet after the Earth. You spoke recently about the ancient dried up riverbeds of Mars, and it just has me curious whether we know anything about the ancient 3 whatever billion years ago atmosphere of Mars and its composition and thickness. Also, whether there were plate tectonics on Mars at that time. As you have mentioned, there are not at present. And just so as you know, in my current science fiction work in progress, a training base for interstellar astronauts located on Mars is named after Dr. Fred Watson, because, as he has pointed out in response to my previous silly questions, there is actually no point whatsoever in having such bases on Mars and other planets. Can't wait for the answer. Berman Gorvine over and out.
Thank you, Martin. Oh, dear. Okay. Yes. We're talking Mars a few billion years ago. What was it like atmospherically?
So the thinking is that it was, as it is now, rich in carbon dioxide, but much higher pressure. Now, if it had life, that might have changed it a bit, because living organisms modify atmospheres. But I think the investigations that are currently going on with, the likes of Curiosity and Perseverance, the 2 Mars rovers that are currently active on Mars, I think there's a good chance that we will know more about the atmosphere of Mars from the research that they've done. And I think the real turning point is going to be when, as I hope we will someday, when we get samples returned from Perseverance, which has been caching little rock samples, I think 17 or 18 of them now, there might be more than that, in little cylinders, to be brought home by a future mission, on which work is currently going on. It's a joint European Space Agency NASA mission, which I think has been scrutinized recently by Congress, and I don't think they were that impressed with progress. So that's something that we might need to keep an eye on. But I know work is continuing.
Sorry, you'll just have to backtrack a bit because you dropped out again. So
that's not very good, is it? I wonder why that's happening.
Don't know.
Anyway, where do you want me to start from, Andrew?
I didn't quite catch where you were going with the question, so I can't really indicate what you were about to say.
Yes, let me summarise by saying that we might know more about Mars's past atmosphere when we receive samples back from Perseverance, which are already on the Martian surface. It's taken little samples of the rocks, which are for future analysis by Earth-based laboratories when they come back. At the moment, I think that mission is planned for 2033, but work is still ongoing with that.
Okay. Now, what about plate tectonics? We know that there's no real movement within Mars now, but did it ever have plate tectonics?
Good question. The reason why I'm doubtful about this is that there's evidence both ways. I think it may well have had at least crustal plates. So the evidence for a solid crust comes from a number of aspects, but one of them is the size of Olympus Mons, which is a volcano that is 23 kilometers high, is it, compared with 10 kilometers from Mauna Kea, the tallest volcano on our planet. It is thought to have been formed by a hotspot in Mars's mantle, but because the crust wasn't moving at all over that hotspot, it just kept pumping stuff out at the same place. Unlike the Hawaiian chain of islands, which are dotted along a line because they're being carried along by the crustal movement of the Pacific plate.
Yeah.
So you've got this succession of places where the hotspot has burst through and produced volcanoes. Unlike that, on Mars, you've just got one spot. It doesn't move. And so this stuff is generating a large volcano over a long period of time. Now, what makes me think that there may have been plate tectonics very early in Mars's history is that I think there are traces of magnetism along linear features on Mars, which may have been the old plate boundaries. So maybe when Mars was hotter than it is now, at an earlier time in its history, its mantle had enough convection in it to cause plate tectonics to be happening. But they stopped, and their fossilized remains are what we see in some of the magnetic fields.
Right. There are certain activities on Mars that are inexplicable even today, and that is some of the emissions that are being detected.
Yeah. Methane.
Still trying to figure that out.
Yeah, that's a good point. So something might still be happening deep under the surface. But the thinking is it's not the core of Mars is too small for its heat to support plate tectonics.
Right. There you are, Martin. Good questions. And we do think in Mars's deep, dark past there was liquid water for a brief time, don't we?
Yeah, absolutely. The evidence for that seems to be incontrovertible. So that we've got a period which may have lasted, it could have lasted for the better part of 1 billion years. And that's long enough probably for living organisms to generate if they're going to. And that's why there's so much excitement in these samples that we would like to see coming back from Perseverance, because they may contain evidence of those living organisms.
Sorry, you'll have to just do that bit again. There was so much excitement, I think you were about to say.
I did say it.
Yeah, we didn't. I didn't hear
we
it.
dropped out.
Yeah.
I could see you actually froze there as well. So there is something going on. Sorry, Andrew. So the excitement, yes. So there may have been. So if Mars was warm and wet for up to 1 billion years, that may have been long enough for life to form, and that's why there's so much excitement in awaiting the samples that Perseverance has been collecting, which one day we hope will come back to Earth.
Yeah, we certainly hope so, and hopefully it's not too long. We really want to know the answers. Thank you, Martin. Looking forward to the book with the Fred Watson Mars base front and centre. Yeah. How do you feel about that, Fred? Iconic.
I'll take it however it comes. It's funny actually, because I was reading the last chapter of my book Stargazer, which is about the history of telescopes. I'd forgotten this, but I set it, the last chapter, on the 500th birthday of the telescope, which will be in 2108.
Oh,
And
wow.
I was looking back at what has happened in the rest of the 20th century in astronomy. And one or two of the things are not far off the mark, actually. But I did mention that it was commonplace for astronauts to visit the Mandela base on Mars. So it wasn't the Fred Watson base, I'm afraid.
Mandela base.
Yeah.
Love it.
Yeah.
All right. Thanks, Martin. Now we'll go to a question from Robert, who is not the same Robert as before. This is Robert from Norway. Hi, this is Robert from Norway. Oh, I was right. With a potentially pointless question about dark matter, dark energy. I'm thinking about frequencies and waves. In audio mixing, there's phase cancellation, when equal sound waves can reduce or eliminate the sound. Maybe the silence that's created actually is a new sound wave that could be called dark sound. And so could dark matter be invisible because whatever frequencies it would need to interact with us have been cancelled out? Or is this all nonsense? And it's more realistic that it just exists in a realm of frequencies we're unable to observe. Similarly, could dark energy be the byproduct of high energy interactions throughout the universe, such as antimatter and matter collisions, creating gamma rays where the opposite effect is dark energy? But that would mean such dramatic incidents are happening exponentially, which probably isn't the case. Please help. I've trapped myself. Love the show. Keep up the good work. I think we've all trapped ourselves, Robert, to be honest.
Somewhere along the line, these arguments all end up in a trap, don't they? Look, I really like Robert's thinking with frequencies, with waves. And of course, just as with sound waves, we use this cancelling effect in light and radio radiation as well. Interferometry, it's called, where radio waves or light waves actually cancel each other out and produce darkness or radio silence. It's how most radio telescopes work, in fact. They're interferometers, where you measure these bright and dark patches caused by the addition and subtraction of light waves with one another, or radio waves. So it's a well-known and well-understood technique. But I like the idea of calling it dark, dark sound. If you've got cancellation of sound waves, do you produce dark sound? And I think the answer has to be no. And it goes on to what, at least in relation to it being an analogue of dark energy. Dark matter. Or dark energy. I can't remember which one he was talking about. I think it was dark energy. So that you've got cancellation causing some sort of dark thing that carries energy. The thing is that whatever dark energy is, there will be a time, I suspect, in the future where we talk about the dark energy field and maybe talk about it in terms of subatomic particles, because waves and particles are essentially interchangeable. And so what would be the frequencies of dark energy particles? That's a really interesting question. And I'm not sure about the cancellation of this sort of thing. I think if you're cancelling waves out, you're going to have nothing rather than some new phenomenon that has just darkness.
Yeah.
But I've got myself in a trap there as well now.
I've actually experienced radio waves cancelling each other out at home, when not in this place, but in our previous house. We used to have a transmitter that would transmit what was on one TV to the other in the house.
Yeah.
It was on exactly the same frequency as the garage door opener. So it was on all the time. Yeah. And so whenever we tried to open the garage door, we couldn't, because the frequencies muted each other.
There you go.
Yeah.
There you go. Yeah.
It wasn't much fun. And it took me ages to figure out what was going on.
Yeah.
For a while there, we thought someone else nearby had the same frequency on their garage door opener.
Oh, yeah. That's interfering as well.
But it turned out to be the TV transmitter in the house, sending the picture to the other TV. Simple as that.
Yeah. I've noticed a couple of times, if you go to the Black Mountain Tower in Canberra, which is a radio antenna producing frequencies of all kinds, I noticed every time I went there that my, the remote car key lock wouldn't work.
Oh, right.
And I wonder if it's the same sort of thing.
It might be.
Cancellation of the radio frequency.
I think you probably got it. Yes. It's as simple as that. All right. Thank you, Robert. Lovely to hear from you. We're just about done, but we've got a little treat in store for you. And I might regret this, but about 5 episodes ago, one Martin Berman-Gorvine sent us a song. And I said, Paul hasn't sent us a song for some time, so guess what's about to happen, Fred?
Looks so we might be being entertained.
If you want to call it that.
G'day, Fred. G'day, Andrew. It's Paul from Bris Vegas. Andrew, you asked for it. Here it is. Second planet from the sun, hotter than a Vindaloo. Yeah, what? What?
I don't want to hear you.
Oh, yeah. Fair enough. Okay. All right. I'll just ask my question normally. Okay. So here it is. So a team from Texas looking through the the James Webb Space Telescope, had a look at JHGS Z13-0, Z12-0, and Z11-0, and they were apparently originally identified as galaxies, but now they think they might be dark stars. So, made of dark matter. If so, how the heck do they produce ordinary photons? Like, wouldn't they produce dark photons? Or is it just the case that when you're squeezing stuff together, lots of matter together in stars, you produce a lot of heat, and it's the heat itself that actually produces the photons? Is that how it works? Oh. So if so, does that mean when we rub our hands together and make them nice and hot, we're producing heat? And so are we producing photons? And if so, does that mean we've got like 2 potential lightsabers at the end of our hands? Really cool if it is. Anyway, guys, keep doing a great job. Have a good one. See ya.
Thank you, Paul. I was more interested in the music version of the question, and that's okay. So if we do this, are we producing photons? Maybe infrared ones?
You are, absolutely. You are.
I got one right.
Yeah, you are. Wavelength of about 10 microns there. That's the temperature of the human body. You increase your temperature a little bit on your hands, and your hands will glow more brightly in an infrared camera because you're producing infrared photons. The answer to Paul's question, though, and I think we did cover this when we talked about those dark matter stars, is that they don't just contain dark matter; they also contain normal matter, because it's the dark matter that sort of generates the gravitational center as it coalesces together, and you take normal matter with it, which is kind of compressed as a byproduct on the way. And the other thing was that the dark matter particles are self-annihilating, so they are themselves radiating energy, which is exciting the normal matter to become visible. I think that was the story, if I remember rightly. So it's actually the glowing that you see from the dark matter star comes from normal matter rather than the dark matter. And what gives it away as a dark matter star is it's much, much bigger than a normal star ever could be. It's wildly bigger than the size of the solar system.
As a matter of fact. Boom,
Indeed. But it doesn't matter.
No, I knew you'd. If you didn't say it, I would have.
Yeah.
Oh, dear. Yeah, look, it's still a work in progress, that dark matter star theory, though, isn't it?
It is indeed, yeah. But I love Paul's musical question. That's great.
Yeah, it was pretty good. Who'll be next, I wonder? Thank you, Paul. Great to hear from you and your offspring, who obviously don't appreciate your talent, and I don't understand why. That brings us to the end of the show, Fred. Oh, by the way, if you do have questions for us, please send them in. We'd love to hear from you. Just go to our website, spacenutspodcast.com or spacenuts.io, and there are links there to send us text and audio questions, the AMA tab at the top, or the send us your voice message on the right-hand side. Don't forget to tell us who you are and where you're from before you ask the question so that we know who to credit. Fred, thanks as always. Been a great pleasure and good fun. A few questions of similar ilk today, but lots of variety as well. Glad we were able to do a history lesson with Buddy, by the way.
Yes. Quite so.
All right, Fred, thanks so much. We'll see you next time.
Sounds good. Thank you, Andrew. Take care.
You too. Fred Watson, astronomer at large, and thanks to Hugh in the studio. Don't know why, but anyway, he might turn up next week. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.